Hi everyone. In this video, we're going to be talking about isotopes, what they are, how we define them, and how we write them chemically. So this is a hard-hitting video when it comes to content that you just got to know for the Regents exam. So make sure you're comfortable with really all the ideas and definitions that we come up with in the next few minutes. So what I've got in blue across the top of the screen are three nuclei of three different atoms. And you'll see that across those three nuclei, there are some things that are similar and there are some things that are different. So if we take a look at those similarities and differences, the first thing that stands out to me is that in all three nuclei, there are 5 positively charged protons. So these three nuclei have the same number of protons, and that happens to be 5, right? If we know that these are all atoms, not ions, we also should hypothetically know that they have the same number of electrons. This is something that, in this case, we're assuming because it's not explicitly written in the diagram, but if we are assuming that these are atoms, we should know that there will also be 5 electrons present to make sure that all 3 atoms are indeed neutral and not charged like an ion. What we also know is that if these 3 atoms all have 5 protons, they all have the same nuclear charge, because the nuclear charge is directly related to the number of protons. And we know that the charge in the nucleus is positive because of those 5 positively charged protons that are present. But the similarities kind of end there. And then we need to start looking at the differences. So what I distinctly see is that we increase our number of neutrons as we move from left to right. So across those 3 nuclei, I see a different number of neutrons. And as a result of that different number of neutrons, we know that these 3 atoms must have different mass numbers, because we know that the mass of an atom comes from its number of protons and its number of neutrons. So all 3 of these atoms are going to have different mass numbers because they happen to have a different number of neutrons. And what we're going to find is that those similarities and differences are enough to constitute what we call isotopes. And I'm going to start writing something in isotopic notation in order to start describing what an isotope really looks like and what it is. So these are both examples of isotopic notation. This is going to be usually more common because it's going to mirror what you see on your periodic table when we're looking up what different elements are. So this X symbol is just going to be our element symbol. And we'll have to know exactly how to look up, symbol. Sorry. We're going to have to know exactly how to look up what symbol an element has on our periodic table. And what's going to help us to do that are these terms A and B over here. B represents our number of protons. And this is going to be key, because what the number of protons tells us is what our element actually is. It's got a different name on your periodic table. If you take a look at the key, when I see an element symbol in the bottom left-hand corner, I see something called the atomic number. This isotopic notation mirrors that setup. So the number of protons I'm going to henceforth refer to as the atomic number. So in this instance, I know I've got 5 protons. So element-wise, what I must have is the element that has an atomic number of 5, which in this case is boron. So I know for all 3 of my atoms, what I've got is something with an atomic number of 5, which means all 3 atoms are atoms of boron. This piece up here, represented by A, is going to tell us about this right here, our mass number. So A represents protons and neutrons in our atom, because they're both important in determining our mass number. So A represents our mass number. So when we look at those 3 atoms across the top again, I see that the first one has a mass of 5 plus 4, or 9. The second one, 5 plus 5, 10. And the third one, 5 plus 6, 11. And now when I'm looking at this particular notation, I see that what I've really got are 3 nuclei of the same element that have differences in their mass. And that is the definition of an isotope. So when you see this term isotope, what it really means is that isotopes are the same element with different masses. And both of these kind of identifiers have specific rationales when it comes to subatomic particles. What I mean by that is that if we're the same element, we've got the same number of protons. And if we're isotopes of the same element, in order to have a different mass, we must have different number of neutrons. And that's what defines an isotope of the same element. You're stuck with the same number of protons, but you're shifting around your number of neutrons to get to a different mass. And there's another way that we can write out isotopes in a slightly different notation than this. Again, this is going to be very common, and you're going to need to know how to interpret this type of notation. But what you might also see is it's sort of simplified down, because if we know the element identity, we already know the atomic number because we've got a periodic table to tell us the atomic number of every single element we've got. And that's always going to be the number here in bold on your periodic table and your reference tables. So what I might see, instead of writing B with the 9 and the 5 to the left, I might write B-9. This is another way of representing an isotope, saying that it's boron with a mass number of 9. So if I wanted to represent the second isotope of boron, I'd write boron with a mass of 10. The third one would be boron with a mass of 11. And here again, I can see that it matches my definition of isotopes of the same element because they're boron all the way across, but they've got 3 different masses. And one thing you'll need to be comfortable doing is kind of working in reverse from this notation back up to what the nucleus must look like. Because if I've got an atomic number of 5, I know I must have 5 protons. But if I didn't know that there were 4 neutrons, what I could do is say that because I have a mass of 9, and that mass comes from my protons plus my neutrons, if I get rid of 5 atomic mass units, that leaves me with 4, which means I must have 4 neutrons in my atom to account for that extra mass. So I can work backwards from my notation to figure out how many neutrons must have been in the original element. We can do it again for this boron with a mass of 11. I know I have a total mass of 11 coming from protons and neutrons, so let's get rid of the mass that's taken care of by the 5 protons. That leaves me with 6 neutrons. And sure enough, in my original nucleus, I've got 6 neutrons. So be familiar with representations, vocabulary, notations, and certainly the definition of what an isotope of the same element really is.